Hello. In this tutorial, I'll talk about activation functions, which are used in deep learning. I highly recommend this book to dig deeper. Deep Learning Illustrated, a visual interactive guide to artificial intelligence. Most of the figures were taken from this book, and you can find the code in this GitHub repo. First of all, why we need activation functions? To introduce nonlinearity. Without activation functions, a neural network could just be a stack of linear transformations. That means no matter how many layers you add to the model, it could only learn straight line. Activation functions add on nonlinearity, allowing the network to model complex patterns. Another point is decision boundaries beyond straight lines. A perceptron without activation can only separate classes with a line or a plane. With activations, the network can learn curves, circles, or any complex boundary. Number 3, to control output range. Some activations squash the outputs into specific ranges. For example, sigmoid, which I will show you a piece of code using sigmoid, the output will be between 0 and 1. This is useful for binary or for probabilities. The tan, the output between -1 and 1, ReLU outputs 0 for negatives and linear for positives. And I will show you these two in later videos. To enable gradient-based learning, during backpropagation, we need derivatives. Activation functions are designed to be differentiable, so gradients can flow through the network and update weights. Without them, training deep learning networks would fail. So this is the graph of the perceptron. Although it provides relatively uncomplicated introduction to artificial neurons, it is not used widely today. It just outputs 0 or 1, and there is a jump sudden here in this 0. This is the equation, which is W to represent the weights, and X the features, and this is the bias term, equals Z. The perceptron's transition from outputting 0 to outputting 1 happens suddenly, making it challenging to gentle tune W and B to match a desired output. So here the sigmoid function is my first example of an artificial neuron activation function, provides an alternative to the erratic behavior of the perceptron. A gentle curve from 0 to 1. This particular curve shape is called sigmoid function. This is the equation of sigmoid function. So the Z is equivalent to W, the dot product between the weights and the features, W and X, plus the bias. And E is the mathematical constant beginning in 2.7. So this is the sigmoid function. As you can see, there is a gentle here, not a sudden jump from 0 to 1. Sigmoid applies slowly to binary problems. For example, either the output is a hot dog or not a hot dog. The only dependency in the notebook is a constant E. This is the method of sigmoid. For example, sigmoid of this number will give me this output, and the sigmoid of negative number will be approach to 0. Any artificial neuron that features the sigmoid function as its activation function is called a sigmoid neuron, and the advantage of these over the perceptron should now be tangible. Small gradual changes in a given sigmoid neuron's parameters W or the B bias cause small gradual changes in Z, thereby producing similarly gradual changes in the neuron's activation. A, which is the activation function. Large negative or large positive values of Z illustrate an exception. At extreme Z values, sigmoid neurons like perceptron will output zeros or ones, as you can see here. This is extreme positives will give 1, and here the extreme negative will give 0. So here it is similar to perceptron behavior. The summary from this video: we need activation functions to make networks nonlinear, learn complex patterns, output meaningful ranges, and allow gradients to flow for learning. And I will talk about these in details in later videos. Thank you.